Imagine splitting a single chocolate ball into pieces and then, without any stretching or deformation, rearranging those pieces to form two identical chocolate balls. Sounds impossible, right? Welcome to the Banach-Tarski Paradox. In the world of mathematics, the impossible often becomes possible. This paradox, named after the mathematicians Stefan Banach and Alfred Tarski, does just that. It challenges our understanding of reality with a seemingly absurd claim. Banach and Tarski, two brilliant minds of the early 20th century, introduced a paradox that left mathematicians and philosophers alike scratching their heads. The paradox posits that you can take a solid ball, break it down into a finite number of non-overlapping pieces, and then reassemble those pieces into not one, but two solid balls identical to the original. No stretching, no deformation, just simple reassembly. It defies intuition, doesn't it? But it's not magic, it's mathematics. So, buckle up as we dive into this mind-bending paradox and uncover the mathematics that makes the impossible possible. At the heart of the Banach-Tarski Paradox lies the concept of non-measurable sets. These are sets that, in the simplest terms, defy conventional measurement. They don't fit into our usual understanding of size or volume. Imagine trying to measure the coastline of a country. Depending on the length of your measuring stick, the outcome may vary. This is a hint at the baffling world of non-measurable sets. So why are non-measurable sets so important to our paradox? Well, the Banach-Tarski Paradox operates in a realm where ordinary intuition about size and volume doesn't apply. It's in this strange world that we can take a sphere, divide it into non-measurable sets, and then reassemble them into two identical spheres. These sets are the building blocks of our paradox, the pieces of the puzzle that challenge our understanding of reality. Now that we've understood non-measurable sets, let's introduce another key player in our paradox, the axiom of choice. The axiom of choice, a fundamental principle in set theory, gives us the liberty to select elements from collections of sets. Imagine you have countless boxes, each filled with countless balls of different sizes. Now, without peeking, you need to pick one ball from each box. In the everyday world, this would be impossible. But in the realm of abstract set theory, where infinity is just another number, this is where the axiom of choice steps in. It says, go ahead, make your choice. It doesn't matter how many boxes or balls there are, you can always make a selection. In the Banach-Tarski Paradox, the axiom of choice is the magical tool that allows us to divide a sphere into those odd, non-measurable sets. It's like a mathematical genie that grants us the power to perform tasks that would otherwise be impossible. With the axiom of choice and non-measurable sets, we have the ingredients for our paradox. But what does it all mean? The Banach-Tarski Paradox isn't about creating physical objects out of thin air, but rather exploring the properties of mathematical constructs. Now let's debunk a common misconception. This paradox doesn't have practical implications in the real world. We can't simply chop up an apple and magically have two. It's a thought experiment that toys with our understanding of space, volume, and infinity. The Banach-Tarski Paradox thrusts us into the philosophical deep end, challenging our grasp of infinity and set theory. It's a mind-bending reminder that mathematics is not always intuitively satisfying. In the infinite world of mathematics, it seems, 1 + 1 can indeed equal 3. This paradox also stirs controversy in set theory. It relies heavily on the axiom of choice, a principle that, while widely accepted, remains contentious for producing such counterintuitive results. So we've divided a sphere into pieces and reassembled them to form two spheres. But what does this paradox tell us about the nature of mathematics and its relationship with the physical world? The Banach-Tarski Paradox challenges our intuition and forces us to question our understanding of the world. We've journeyed through the paradox's central idea, dividing a sphere into pieces that can be reassembled to form two identical spheres. We've delved into the minds of Banach and Tarski, the mathematicians behind this mind-boggling concept. We've navigated the complex waters of non-measurable sets and the axiom of choice, both of which are key to unraveling this paradox. We've debunked common misconceptions, clarified that this paradox has no practical implications in the real world, and contemplated its philosophical and mathematical implications. But remember, the Banach-Tarski Paradox is not about creating physical objects. It's about exploring the properties of mathematical constructs. That's it for today's journey into the paradoxical world of mathematics. Remember, math is not always what it seems. So what other paradoxes out there have you scratching your head? Share, like, and subscribe for more intriguing mathematical explorations.